going to mean something to everybody in the room. So for today, we're going to be focusing on temperatures on the range of about 1,000 to 10,000 Kelvin and pressures in the range of about 1 to 100 gigapascals or so, or this orange blob here, which at least from my perspective is the thermodynamic sweet spot for interesting phenomena, and that your materials are hot enough and compressed enough to start reacting and undergoing other interesting phenomena, while at the same time not being so hot that everything dissociates into a plasma or so high pressure that everything is confined into the solid state. So you might be asking yourself, why is a chemical engineering professor focused on, these sorts of conditions? And the answer to this question comes down to the fact that our group is interested in synthesis science, and in particular in advancing or helping develop new synthesis techniques that can be used to produce materials very rapidly and in a tunable fashion. And so techniques we might consider on any given day will include things like ion beam implantation, laser powder bed fusion, so that's how we 3D print metals, laser shock methods, this is an example of laser peening that can be used to heal defects, sonication, which is a technique used for synthesizing nanomaterials, and so on. And so if you look at these different methods I have here, they all share a few common traits. Number one, they all work. Two, they're all used rather frequently. Three, they all work by driving the material to an extreme temperature and pressure in a localized region over a very short time scale. And four, while we know that these techniques work, we have a very limited understanding of the atomic sort of scale phenomena that are actually taking place. So as I tune my experimental knobs, what effect is that imparting that gives me the final product that I see on the other end? And so from a practical standpoint, this means there is a lot of trial and error that goes into deploying these techniques for new material systems. And so what we're interested in is using simulations to try to fill that knowledge gap, providing those atomically resolved insights that can be used to either, again, make these more tunable or to help develop even more effective material synthesis strategies. I'm going to see if I can get rid of this OK box at the top of my slide here. Let's see. There we go. Okay, so how are we going to do this? We're going to be using a simulation technique called molecular dynamics. We like this technique because it's very simple. So in order to get going, you don't really need to know too much about the system or the phenomena that you want to study. You just really need an initial set of coordinates for your system. So this can be the crystal structure for a material that you want to study. And then some interatomic model that describes how the interactions in your system change as you change your atom positions. And so given this information, you can apply Newton's equation of motion to predict how the system will evolve in time. And so you can quite literally watch the system evolution atom by atom. Or you can sort of post-process the simulation trajectory to learn detailed information about the dynamic evolution of the system, the thermochemistry, the equation of state, material strength, and the like. And so all in all, a very convenient research tool. That being said, the utility of these predictions and the accuracy of these predictions is very strongly linked to the quality of the interatomic model that underlies them. So we are trying to avoid a sort of garbage in, garbage out scenario. And for that reason, it's very important to pay attention to the models that you select for a given target application. So let's maybe talk about this. So what we are trying to do in my group is to use simulations to predict the structure, dynamics, speciation, and kinetics in material and chemical systems as they evolve under very highly non-equilibrium and extreme conditions. And so what we need our model to do is a couple of things. It needs to work under high temperature and pressure. It needs to be able to describe chemistry because that's a very common phenomena under the conditions that we care about. But we also need these models to work on relatively large spatiotemporal scales, as many of the phenomena that we are going to be interested in have nanoscale or even microscale structure to them. And so to give you a sense of what I'm talking about, this is a figure that I stole from one of my former colleagues, Matt Krumblad. And in this top image here, what he's done is to take a molecular crystal of an explosive compound, and he sent a shockwave through it. So you can see the shock has gone from left to right and is now exiting the material. And it's left in its wake these yellow striations that are localized regions of enhanced disorder, so nominal shear bands, that also happen to be thermally activated. And so it's within these features that the chemistry that ultimately can give rise to a detonation event can nucleate. And so if we want to understand that process, we need simulations large enough to resolve these several tens of nanometers long and roughly 10 nanometer wide features And at the same time, we need our model to be able to describe the atomically resolved chemistry that's happening within these features. So at the time that we started the work that I'll talk about today, we had really two choices available to us. We could use first principles based methods, which you're going to hear me call quantum mechanics and DFT throughout this presentation, which are very, very predictive, but they're also very computationally intensive. And so we fundamentally cannot apply it to problems of this scale. On the other hand, we can use classic reactive interatomic models where these are relatively simple analytical expressions that some subject matter expert will write down. They'll say, I think, charge interactions are important for this system. And I think that, bonding interactions are important. And you write down your set of equations and you come up with a model that's very computationally efficient. You can run simulations like the one I'm showing here. But now the problem is that when we are talking about systems driven to these far from equilibrium and extreme conditions, especially systems that are reacting, we don't really know a priori what those equations should look like. And so we can make models, but their accuracy tends to be dubious when applied to the sort of problems that we care about. And so we were left with this accuracy computational efficiency gap. Right. So this is where the machine learning comes into this presentation. So we decided to develop what are called machine learned interatomic models to bridge this capability gap. And so what I'm going to do in the next couple of slides is tell you a little bit about how we do this. And then when we end that story, we'll talk a little bit about some of the science that we can use these models for. So again, this is work that started back when I was a postdoc at Lawrence Livermore National Lab. And so this is the team of folks that have contributed to this from Livermore over the years. And now for the work that I'll highlight today, these are two of the students that are working on this in my lab at Michigan. So these days, if you throw a dart, you're going to land on about 5 different machine learned interatomic models. This was not the case when we started on this endeavor. And so I laid out on the previous slide this idea of certain criteria that we need or certain goals we have. We want to be able to describe condensed phase chemistry under extreme conditions on very large spatiotemporal scales. And so there were maybe 3 or 4 ML potentials out there, none of which were designed to solve that specific problem. And so we decided to develop our own that we call CHIMES for the Chebyshev interaction model for efficient simulations. So CHIMES is a relatively simple physics-informed machine learned interatomic model. So this is our overall system energy equation, where this is just a many-body cluster expansion. So total system energy comes from the sum over interactions for monomers and dimers and trimers and tetramers, up to some arbitrary bodiedness. And we're going to use an expression that looks like the following to write down what these n-body interaction terms are. And so the only thing you need to take from this expression is that we use Chebyshev polynomials as our basis functions. That's what we've highlighted in purple. And then in pink, this product symbol here is basically telling you that when we deal with many-body interactions, we treat them as the product of interactions for constituent atom pairs. So if any of you on this call are simulators and work with these ML potentials, the other way I can describe this is Chebyshev polynomials are our basis functions, and our descriptor is essentially the fully connected graph between the atoms that comprise our n-body cluster. Okay, so let's make this simpler. What I'm showing here is the expression you get for a 2-body interaction. And so each one of these t's is a polynomial of subscripted order. The argument S is a transformation of the distance between a given pair of atoms, and then the coefficients out front are what we fit when we talk about fitting these machine learning potentials. And so what do we train these things to? What we're going to do is to run short first principles multidynamic simulations or calculations that give us data that look like coordinates for a system with the per atom forces, an overall system energy, and a system stress tensor. And so our goal is to adjust these parameters such that given the same input, our model predicts the same output. So ultimately, this is a way to develop models that can be viewed as a computationally efficient proxy for first principles calculations. And so I'm going to claim that these models are quantum accurate or capable of quantum accuracy, and I'll put some numbers to that in a moment. But because these models are really simple, these don't look like the popular sort of neural network-based approaches. This means we can fit them very quickly, and we don't need nearly as much training data to do that. So they're also just very efficient. Okay, so I claim this thing is quantum accurate. What do I mean by that? So recently we published a paper where we were using chimes to look at shock-induced chemistry in nitrogen. We also wanted to look at what happens when you reshock nitrogen, because there's some interesting speculation about shock-induced cooling. And so the first step of this process was to build and validate a chimes model. And so here's some of the data that we look at. So as I go across a given row, this is data for a given state point. Um, and so we go from nominally ambient conditions to 8,000 Kelvin and what turns out to be roughly 200 gigapascals. This first column, these are radial pair distribution functions. So they tell us about system structure. And in this column over here, these are vibrational power spectra, which tell us about the vibrational modes in our system. And the point here is that there are two sets of data in each plot. There is gray data, that is our first principles reference data, and then the black dashed data is our chimes prediction. And you probably can't tell that there's two data sets there because they're right on top of each other. So that's what we mean when we say quantum accurate. We can also compare these things to experimental data. So here we use this model to predict the shock Hugonio for nitrogen. And so now if you look at the up and down triangles that start about here and end about here, these are experimental predictions. And then these open circles are what chimes predicts. And so we can validate against experiment. And then we can take this a step further and say, well, why don't I dig into my simulation and provide information on the time-resolved structural evolution or the time-resolved chemistry that takes place during this shock compression, for example. So just to kind of give you a sense of things. All right, so chimes has turned out to be a really important tool for us. In my group, every student in my lab is either using chimes for applications research or developing advancements to chimes. And it's giving us access to problems that we wouldn't have been able to solve before or even study really effectively before. And so I'll talk about this guy over here later on in my presentation where we use chimes to study shockwave-driven nanocarbon synthesis effectively. But this is another study where we use chimes to do something kind of for the first time. And this was to look at shock-induced detonation of an explosive compound. These are using direct shock simulations for any of you simulators using an ML potential. So why is that interesting? We, meaning the community, have been running simulations like this for forever using those sort of classical underatomic models I mentioned early in my presentation. But that came with the caveat that, again, the accuracy, especially the chemistry, the equation of state, and so on, coming from those models can be dubious. And so this really represented the first time we were able to look at a phenomenon like this and know that the chemistry that we were getting out was nominally quantum accurate. And so that makes these predictions a lot more sort of practically useful. All right. So I have one more slide on chimes, and then we'll move on to our science story. And this slide is more for those of you in the audience that might be simulators and interested in using tools like this. So if you look at our early publications in the chime space, a lot of those papers were us convincing ourselves that this technique works. And so you'll see a lot of models generated for a lot of different systems. We have since then convinced ourselves that yes, this does work quite well. It's generalizable to problems even outside the sort of extreme conditions area. And so a lot of the work that we've been doing in this space recently focuses more on making this tool broadly accessible to the modeling community. And so that means building up a lot of the workflows and the AI and the ML that underlies development of these models. And so, we have some papers that have been published and are also, of course, developing new capabilities to help improve the automation for training. So to make it easier for you to go from a data set to a production-worthy model, reproducibility and trustworthiness. So building uncertainty quantification into our workflows, because again, we want to make sure we're not producing garbage. Improving training efficiency, so reducing the size of the data sets you need to build these models, for example, is one way that we are doing this. And then working towards extensibility. So if somebody wants to simulate a system similar to what we've looked like in the past, maybe it has a new element in it, you don't need to start from scratch in terms of developing a model. So if this is something that you're interested in, keep an eye out. We're always sort of trying to push out new methods to the community, and we're also happy to help anybody that wants to, wet their feet with these tools and might need a little bit of guidance. Okay. So we've talked about sort of the problems that we care about, understanding fundamental behavior of materials under extreme and far from equilibrium conditions, using those insights to advance synthesis science by way of either helping refine control in pre-existing high pressure, high throughput methods, or developing new techniques. We talked about how we do this. So we use molecular dynamics simulations, and we make sure that we can access the spatiotemporal scales that we're interested in with the accuracy that we need through these machine learning interatomic potentials. So let me show you an example of some work that we have done with this. Okay. So again, this is a project I started back as a postdoc. And so over here we have the Livermore team that has been involved in this. And now the torch has been passed to my student, Yan Jun, who is working on this nowadays. And again, what we're focused on here is trying to develop a laser shock-based method for nanocarbon synthesis. So what is this about? Okay. So when I was at Livermore, I worked in the Energetic Materials Center, which is an explosives research group. That was a pretty big pivot from my background area. And so I was learning a lot about a new field. And one of the things that stuck out to me was the following. If you have a carbon-rich explosive and you detonate it, you are likely to form nanocarbon particles. And in fact, as you change what your explosive, let's call it a precursor, is, you'll get different kinds of carbon nanomaterials. So this over here is something called Comp B. It's a mixture of RDX and TNT. And when you detonate this, you form nanodiamonds. And in fact, industrially, this is how nanodiamond is produced. This guy over here is called DNTF, and he forms graphitic nanoonions. And we'll talk a little bit more about those toward the end of my presentation. And this is picric acid, and it forms these glassy nanocarbon particles. And so from the standpoint of energetic materials research, it's important to understand this phenomena because it has implications for the performance of the materials. However, as I mentioned, I'm interested in material synthesis. And carbon nanomaterials are of tremendous technological interest because they can exhibit a near continuum of physical, chemical, electronic, optoelectronic properties, you name it. And so you can find them in applications spanning from quantum computing to drug delivery and catalysis and so on. Okay, so what's the problem? Um, if you look through how these materials are currently made, you're going to fall into one of two camps. We have our high pressure, or sorry, our high temperature, low pressure techniques. So this could contain things like flame pyrolysis, we'll call this low pressure, so chemical vapor deposition might fall into this category and so on, where what you're going to get is very fine control over your synthesis process and very low throughput. So think microgram of material per hour. On the other hand, we have our high pressure techniques. So this could be things like ball milling, sonication, or the very dramatic example of detonation synthesis that I mentioned before, where now we're talking about throughput in kilogram per microsecond quantities. So very, very high throughput. But the problem here is that this is about as far from tunable as you could possibly imagine. And so in particular, in the case of an energetic or an explosive precursor, what's happening is the detonation of the material imparts a shock wave into the material that drives it to the high temperature and pressure that causes the formation of these nanoparticles. And what that pathway looks like is a function of the chemical nature of your explosive. So if you want to make some material other than, let's say, these three, you're going to have to blow up a bunch of stuff until you find one that happens to make the particle that you want. So not really tunable. Okay, so we had this idea that we can sort of circumvent this by decoupling the source of that shock wave from a detonation. So we can use an external source, like maybe a laser, to impart that shock. That's going to give us complete control over our precursor. So that's great. But now we have this other problem where, despite having known about this phenomena for the better part of better part of a century actually, since the 1950s, the community actually has very little understanding of how this technique works. And the reason for this is that we're dealing with very, very tiny particles, so nano-sized particles that form on very short timescales, so sub-microsecond. And so when you try to track their formation, you end up with data that look like the following. So these are time-resolved small angle X-ray scattering data monitoring detonation-induced nanocarbon synthesis. And you see you have these curves sort of before the experiment takes place that are linear, indicating there are no condensates present in your system. And then you instantaneously transition to this regime over here where there's a knee in these data that indicate the condensates have already formed. So from this sort of measurement, really all you're getting is an upper bound time scale for formation. You're not getting detailed kinetics or underlying mechanisms. And so we became interested in a couple of things. So A, can we design a nanocarbon synthesis technique that draws inspiration from detonation synthesis, but is more tunable? And B, can we use simulations to help sort of elucidate some of the underlying phenomena? So in order to do this, we wanted to start simple. And so we looked through the literature and came across the following study by Nellis and Ree. And so here they ask the question of what happens when you shock compress cryogenic liquid carbon monoxide. And so this is an interesting question because carbon monoxide is the simplest possible material that can undergo this phenomenon. It's carbon rich and oxygen deficient. And so if we look at their data over here, these crosses are experiments. And then these lines here are predictions from different equation of state models. And what we see is that for weak shocks, we end up on this solid curve, which is the non-reacted equation of state. And then for stronger shocks, we find ourselves falling on this curve over here that accounts for the formation of carbon products. And so if you read through this paper, they kind of suggest that this might indicate that nanoparticles are being formed, carbon nanoparticles, but they never really performed any recovery to assess that hypothesis. And so what we wanted to do was see chimes if we could study this system and predict whether or not condensates form. If they do, we can say something about this. And at the same time, we can use this chime study as sort of a feasibility study before trying to have the experimental portion of the team actually build up a platform to do this. So we went about this study. And again, the first step for any chime simulation is build a chimes model. And to build a chimes model, we have to run first principles calculations. And so we decided why not just try to simulate this process with DFT is the method we used in this case, and just see if it tells us anything sort of useful about this process. And so we did that, and we didn't really see anything interesting. And this is because these simulations are for order 100 atoms or so. And you really can't afford to go beyond maybe 10 picoseconds or so with these simulations. And so it's just the simulation sizes are smaller than the size of a single nanoparticle you would expect to see. Okay, so we take the chimes model that we built and we run these simulations where we've now scaled up to over 1 million atoms. And when we do this, a very different picture emerges. So looking at this image, each little red dot you see in here is an oxygen atom, and there's little black dots that are of equivalent size that are our carbon atoms. And what you are watching is formation of a population of roughly 5 nanometer carbon nanoparticles with atomic resolution. So the short of it is that our simulations are predicting that yes, you can indeed use a shockwave to synthesize nanocarbon from a cryogenic liquid carbon monoxide precursor. And so based off of this, the experimental portion of this team, so that would be Mike Armstrong, went ahead and built a tabletop ultrafast laser-driven shock platform that allowed him to conduct the same experiment on the same time scales and overlapping length scales with our simulations. And so here is what he finds. So this is a TEM image of a agglomerate that's comprised of these smaller particles. So these are individual nanoparticles outlined in these semicircles over here. That turned out to be the same size, shape, and chemical composition as what we predicted in our chime simulations, and they form in the same time scales. And so this was a really exciting result, kind of confirming the sort of validity of these machine learning accelerated simulation predictions, which is always great. But perhaps what's more important is that this result gave us the green light to dig into our simulations and try to answer some of the long-standing questions surrounding how this process occurs. And so there were a number of open questions that we wanted to see if we could shed some light on. So first things first, what does this process even look like? What are the overall kinetics of this process? And how does chemistry factor in? So from our simulations, we can do things like extract pictures. So this is a cluster growth timeline where we can see at early time we have these low density extended maybe seed clusters that have oxygen in red and carbon in black distributed roughly homogeneously throughout. And as time goes on, we can see our clusters densify, they sort of agglomerate together, and they form these nice spherical carbon nanoparticles that have oxygen decorated exteriors. Okay, so that's great, but that's not very quantitative. So can we maybe take a more detailed look at this? So what I'm showing here is another sort of view of the picture that I just showed you. So this is a time and radially resolved cluster composition plot. So if I'm sitting at 0, I'm in the middle of one of these particles. As I go outward to, we'll call this 1.25, that's roughly where the interface between the nanoparticle and the reactive soup that sort of solvates it exists. And beyond that, we're moving out into the fluid. And so the solid lines here are telling us about the carbon composition. The dashed lines are telling us about the oxygen composition. And we see at early time, we have this mixture of carbon and oxygen. And as time goes on, we become increasingly pure carbon at the interior. We're pushing out oxygen, and we see that oxygen start to form an enhancement layer on the surface, consistent with that sort of qualitative picture I showed you earlier. And so again, we can characterize the kinetics of purification of these carbon nanoparticles. We can also ask about kinetics on a sort of larger scale. So in this picture, what we're looking at, or this plot over here, we're looking at a cube of the average particle radius as a function of time. And we see there's two regimes here that's kind of difficult to see, but we have an S-shaped regime and then a linear regime. And so this is following along with what we'd expect from classical nucleation kinetics, where this linear regime is telling us we've hit an Ostwald ripening cluster growth mechanism. And so this is cool because already between these two plots, we can start to do some useful things. For example, if somebody says, well, I would like to form a particle of this size and of this composition, we can use the data like this to provide insight on the protocols or the timescales for the experiments that would be needed to achieve that product. Conversely, I mentioned it's very difficult to track what's happening during the experiment. So someone can produce something, characterize the particle, and based off of things like the size and the composition of the particle, we could also provide guidance on how it got there. Okay, so taking this a step further, one of the other questions we had is, what is the role of chemistry? And so again, I mentioned that this linear regime is telling us that our clusters are maturing through an Ostwald ripening mechanism, which means that our big clusters are growing due to our small clusters shrinking. And so that means we have to have a way of transporting carbon between those clusters. And so the previous hypothesis on how this process would work was through dissociation and diffusion. So imagine your carbon monoxide molecule kind of pops apart, and your carbon atoms are wandering around trying to find a carbon nanoparticle to associate itself with. And so if that were the case, you'd expect that if you analyze the fluid that solvates these particles, you'd see a very high concentration of free carbon atoms in it. And so we ran that analysis, and here's what we see. So this is now the time-resolved compositional evolution of the fluid solvating our particles. And we see there's a lot of carbon dioxide. There's a considerable amount of carbon or of oxygen. We have a non-negligible amount of carbon monoxide, but we're really not seeing any free carbon in here. It's basically zero. And so what this is suggesting is that that carbon transport mechanism is likely reaction mediated. And so in fact, what I'm showing here, this little black dot is carbon atom. This is a small carbon nanoparticle. This is a big one. And what we're doing is we're watching this carbon atom move from one cluster to the other. While this carbon atom moves, we're rendering in red any oxygen atoms that are within bonding distance of that carbon atom. And what we find is anytime that particle is at the surface or outside of a particle, it's always existing in a state where it's forming carbon monoxide or carbon dioxide. And so in essence, we have a reaction-mediated transport mechanism. And so this is important because when we look at the slope of this Ostwald ripening curve, the slope is going to be dictated by the kinetics of that chemistry. And so one of the ways that we can actually potentially control the size of the particles that we get would be by modifying the chemistry that's happening in this solution. And so that would go back to saying, well, maybe we want to adjust the composition of our precursor so that we can control that chemistry. And so again, interesting insights that hint at ways that we might control this process. Okay, so by the time we reach this point, I think we were all pretty excited. Again, it seems like this technique will work. We have a kind of proof of concept. We have some simulation analysis that gives us a preliminary sense of what is happening during this process, but there's still a lot of work to do. And so in particular, let me lay out to you what all is happening. So the technique that Mike, our experimental team member, created is doing the following. So he's going to take a liquid precursor that has a high concentration of carbon and use a laser to impart a compressive shock wave in that precursor. That shock wave is, in this case, going to take our system to a high temperature and pressure state that is above the melt line of carbon. And what that's going to do is drive a reaction-driven phase separation of the excess carbon in the precursor from the everything else in that reactive soup that we've created, driving nucleation of these liquid carbon nanoparticles. At some point, that compressive shock wave is going to move out of your sample, and that's going to cause it to adiabatically expand back down to ambient temperature and pressure, and that's going to drive a solidification of those liquid carbon nanoparticles. And the nature of those nanoparticles are going to be controlled by things including the initial state that you quenched from, the rate of that adiabatic expansion, the composition of the particles when you began and are undergoing that expansion, and so on. So it's a pretty complicated process. And so if I'm a little bit more precise, this is a condensed phase, reaction-driven, coupled phase separation and phase transformation process, and we want to understand it. Okay, so if we want to make this process tunable, what do we need to figure out? Well, carbon phase transformation plays a critical role in this process. So we need to be able to answer questions like, where are the phase boundaries in carbon? As I'll touch upon in my next slide, you would think that this is a solved problem, and it's not, part of the reason being how high that melt line is. Once we figure that out, we need to figure out what are the kinetics for phase transformation across those phase boundaries. And the kinetics here matter because the solidification process I talked about is a non-equilibrium process. So we won't necessarily get what the equilibrium phase diagram would suggest we would get for a given thermodynamic quenching pathway. We also need to understand, the impact of surface free energy. And so, we're dealing with finite size systems. And so the result that we get for a nanoparticle and bulk carbon will be different. So that all talks about our carbon phase transformations, but what about chemistry? So this initial reactive phase separation is to some extent a miscibility-driven event. So can we make general claims about miscibility of different mixtures of elements under extreme temperature and pressure? And we talked about the role of chemical composition as well in that carbon transport mechanism. And so can we again establish general principles for how chemical composition sort of modulates all the effects that we have just talked about. So there's a lot of work for us to do. So in the next couple of slides, I'm going to start by trying to address the carbon phase transformation part of this. And then at the end, we'll touch upon some of the chemistry bits. Okay, so this is kind of the state of our understanding of the carbon phase diagram up to 100 gigapascals as of, we'll call it 2008 or so. And so in the shaded gray, what we're looking at is a conservative sort of spread of experimental data that exist out in the literature. And so this portion over here is the graphite melting branch. This is the diamond melting branch. This is the graphite diamond solid phase boundary. And so there's a considerable spread in the data for the graphite melting portion. Again, if I were to draw all the data, it'd be an even larger spread. And part of this is because these measurements are not as direct as one would like. For the diamond melting portion, again, it seems like the data is tapering off at high pressure. This is not because the experiments are getting more precise. It's because there is one experiment reported at this highest pressure. There's two experiments here, and so on. More importantly, the specific temperatures are not measured in those experiments. What you get is the curvature of the slope of the melt line, and you kind of take that melt line and you shift it up and down until it seems like you get a result that's consistent with the expected triple point of the material. And so there's a little bit of finagling that goes into converting those experiments into a phase diagram, especially for the liquid solid portion. The graphite diamond phase boundary is much better constrained. I think this data here is representing two different experiments that are in very, very good agreement with one another. These are lower temperature measurements, so a lot less of the complications manifest there. So now in the dashed lines, what we're looking at is what was the state of the art in computational models back in 2008. This is one of the LC-BOP potentials. And we see that the melt line has a slope that's a little bit steep with respect to the experiments. The graphite melt line is rather low relative to the experiments, and the graphite diamond phase boundary is a little bit off. So we recently developed a new CHIMES carbon model that's designed to work up to about 100 gigapascals and decided to apply it to revisit this problem of the carbon phase diagram. And here is what our data look like. So I'll start with the graphite diamond phase boundary because it's the easiest thing to talk about. It falls right on top of the experimental data. So that is very reassuring, considering, again, this is the data that is the most well constrained. What we're looking at over here, this is our diamond portion. So we are actually consistent with the experimental data here. Our graphite portion is also low relative to the experiments that I'm showing over here, although the slope is doing a little bit better. We have some questions about whether this is an sort of effect of how we ran our simulations or not, but still a fairly good prediction here. So I'll show one other set of predictions. So recently, Yvonne Olenik's group at USF developed a carbon machine learning potential that was designed to work under terapascal pressure, so much, much higher pressures than we look at. But it also works in the range of 50 to 100 gigapascals, which overlaps with our model. And you can see that our diamond melt line lines up essentially perfectly between these two models. And this is really interesting because the machine learning models, so they use something called SNAP. We're using chimes. These are completely different types of ML models. They're trained to completely different data sets. And so the fact that they agree with one another kind of lends credence to the accuracy of these predictions. Okay, so cool. We have a bulk equilibrium phase diagram for carbon. However, as I noted, nothing about the process that we talked about is happening under equilibrium conditions. So the question becomes, what are kinetics going to do to this? And so in particular, we wanted to understand as we go through that sort of quenching, how much can the sort of kinetic nature of that process modulate the solid phase of carbon that we get out on the other end. And so to assess this, basically what we did was to prepare a variety of systems at a variety of densities and a temperature up above the melt line. And then we take that system after it's equilibrated at that high temperature and density, and we rescale the velocity so that the temperature drops to some target temperature below the melt line. So this might look like the following. So these are the three different densities we look at. We run those simulations, and as time goes on, they're going to start to solidify. And based off of the solid phase that we get and the PV curves that are associated with the sort of suite of densities we run these calculations at, we can draw sort of kinetically limiting graphite diamond phase boundary. And so that's basically what this is here. And so again, in these simulations, we've got, amorphous sp2 carbon, we've got graphite. In this simulation, you can see we're starting to nucleate diamond over here. But yeah, so if you take all of our data, we find that this equilibrium graphite diamond phase boundary can be pushed out to about where these stars are. So you can form graphite at pressures as high as 25 GPa, depending on how you do that phase transformation. And so this is interesting from the standpoint of, again, designing how these shock experiments are done to synthesize material. It's also interesting from the standpoint of being able to perform sort of post-mortem analysis. So I've run an experiment. I'm not really sure what the rate of quenching was after my shock. I get this material. What does this tell me about the pathway that I took? So yes. All right, so we've got our bulk equilibrium carbon phase diagram. We have a sense of how this phase diagram can be modulated under non-equilibrium conditions, but the nanoparticles that we're dealing with are finite sized. And so the question becomes, how does this change when we're dealing with these small particles? And so how we're dealing with this is we are taking liquid carbon particles, we put them in a bath of argon. And so we can use that argon bath to squeeze the system to some target pressure, and then we can cook the particles at a target temperature. This went through a little bit quickly. I'll just go back so you can watch this again. And so what we're looking at here, these are two different particles. These are cross sections, 4 nanometer nanoparticles. We're cooking them at 3,500 Kelvin and either 15 or 50 gigapascals. And so we run these simulations and you can see they solidify. So here we get these concentric rings. These are basically those graphitic nano onion shells that you're looking at. And over here we solidify into a nanodiamond. And so we can take this data and we can collate them all to form sort of a nanoparticle phase diagram. So this is what we get from our 4 nanometer simulations that we've done thus far. Of course, the phase diagram that you get is going to be a function of the size of the nanoparticle. So we're running this for a bunch of different system sizes. And so I'm going to show you this 10 nanometer nanoparticle simulation that's at the same pressure as this guy over here. And what I want you to pay attention to is how that solidification begins. In particular, for these two guys over here, the 4 nanometer particles, you basically have a barrierless phase transition. In the case of this large particle, you see something that looks a lot more like a sort of classical nucleation, and that there's a bunch of seeds that form and vanish before you start to get seeds that begin to grow. And so the practical consequence of this that you'll see as the simulation runs is whereas we get a single nice nanodiamond here, you're going to see a lot of nanodiamond grains forming in this that are going to eventually grow and form these boundaries between them. And so understanding the mechanism through which these particles solidify can also give us guidance on how to conduct this quench such that we might be able to avoid having all of these defects in the final nanodiamond particle. Okay, so yes, this is providing valuable insights for interpreting experiments and designing nanocarbon synthesis protocols. So I just have one more example of some work we've been doing that I'll share before I wrap things up. I promised I would talk a little bit about how the chemistry factor comes in here. And so now I want to talk about nitrogen-containing graphitic nanoonions. So what is this about? In the beginning of my this portion of the talk, I discussed this molecule called DNTF that when detonated forms these graphitic nanoonions. So again, if you look carefully at this TEM image, you'll see these concentric rings. Those are the layers of the graphite shells. If you look carefully, it might be difficult to see, but these particles also have a core to them. You can see that there and over here. So for these particles, there were a couple of questions. Number one, how do these things form? Number two, what is in the core of these particles? Now, DNTF is a nitrogen-free explosive, so it's carbon, nitrogen, and oxygen. Our previous simulations for the shocked carbon monoxide shows that carbon and oxygen are very immiscible in one another under the conditions relevant to this process over here. And so if we want to understand how these particles form, we can kind of just ignore the role of oxygen in this process, and we're going to focus on what happens when you have carbon and nitrogen together. So again, how are we getting these graphitic nanoonions? Why do these nanoonions have a core to them, and what is in the core? So what we did was the following. When you detonate a material, it's very similar to what happens during a shock experiment. You're going to reach some sort of peak temperature and pressure. We call that the Chapman-Jagow point. And once you hit that pressure, you're going to sit there for a while, and then everything is going to sort of thermally and mechanically relax to ambient temperature and pressure. So what we did was to take a liquid carbon nanoparticle and prepare it at that Chapman-Jagow point. And we take it and we adiabatically expand it. So it's going to go through the same sort of thermal and pressure quenching pathway as these particles over here would. And so this is what we get. So each one of these particles are at a different time point along that quenching pathway. They're colored by radial position. So red just means you're in the center of the particle and blue means you're at the surface. And what you see, for example, at this 0.45 nanosecond snapshot is that you're forming these layers of this graphitic nanoonion, and you're doing this from the outside in. So that's something interesting that we're going to kind of remember for a moment. So, okay, this is giving us a sense of how the particle solidifies, but what about nitrogen? What's happening with nitrogen and where is it in the particle? So what we did was to prepare a number of simulations at different temperatures and pressures that had a mixture of carbon and nitrogen in it, and we just let those simulations run, and we ask, is the nitrogen and carbon, did they remain miscible? Did they begin to phase separate? And if they do phase separate, what's happening? So this is an example of one of those simulations. So where you see pink, that's a carbon-nitrogen bond. Black is a carbon-carbon, and those little green things rattling around, those are nitrogen molecules. And so in fact, what we found is that for pretty much for most of our simulations at high temperature, these carbon and nitrogen remained very well mixed with one another. It wasn't until we dropped well below where the carbon phase boundary, the melt line would be, that you started to see phase separation. And it happened as this coupled reaction-driven event. So we sort of evolve molecular nitrogen out of our carbon-nitrogen bonds at the same time that we start forming these sort of graphitic sheets. Play that again. And so if you take these two images together, the little snapshot and the movie over here, this suggests the following. When these nanoparticles are formed in the liquid state, they likely have nitrogen in them because our simulations have suggested that nitrogen is very soluble in carbon. As you begin to drop the temperature and the pressure as you adiabatically expand, the particle is going to want to solidify. And as the solidification is happening, that's when your nitrogen would want to come out. However, that solidification is happening from the outside in, which suggests that at least some of that nitrogen has got to get trapped inside of the particle and pushed to the core as you begin to extend that solidification. And so our simulations would suggest that the stuff inside of the core of these particles is likely nitrogen in the molecular form. And so they recently took these particles and did a little bit more analysis where they used in the TEM the electron beam to pop the particles while taking the chemical spectrum of them. And what they found is that the spectrum for the triple-triple bond character in them and the nitrogen signal dropped off when they popped them. And that would be conducive with molecular nitrogen evaporating out of those particles, which is consistent with what our simulations are predicting. So again, we can use these sort of simulations to not only help guide strategies for designing certain materials, but also to help interpret how complex particles like these are formed under shock and detonation conditions. So I will wrap my talk up there. Thank you all so much for listening to me yap for the past 45 minutes. I have just a couple of concluding remarks here. Again, our TIMES capability is really critical in allowing us to do the work that I've talked about today. And, you know, from the science perspective, what we're trying to do with these tools is really advance our understanding of how chemistry couples with phase transformation and phase separation to make these nanocarbon sorts of materials. So hopefully we'll have even more interesting things to say in the near future about that. All of the software that I talked about today is available open source online, and so please check it out if you're interested, and I would be more than happy to answer any questions you may have.
Wow. Thank you, Rebecca, for that fascinating tour through your recent work. We have certainly time for questions. Please either raise your hand or you can type your question in the chat. Yes, go ahead, JZ.
Hi, thanks, Steve. Excellent talk, Rebecca. This is Joe from Livermore. It's good to see you again. It's been a while. I may have missed it, but within your computational knobs, do you have ability to adjust shock-induced strain rate, for example?
Yes, yes, we do.
So have you played with that knob to see what occurred, for example, in any of your examples presented here today or other, made attempts to adjust the shock strain to see what happens?
So this is like upon compression. So sort of, but probably not for the reason that you're thinking. So there's a couple different ways that we can model the shock process. So in some cases, what we're doing is literally taking our sort of portion of material and we're accelerating it into some potential wall that imparts the shock or sends a shock wave back through the material. In that case, you kind of just have whatever your particle velocity is what it is. We have these other methods, so the MSST method that Larry and a few others developed, where you can dial in that strain rate specifically. But the way that we run the simulations, we tend to just say, well, I want it to be high enough that we achieve compression on a certain time scale. And so it's not something we've intentionally looked at the effect of making it like stronger or faster or slower. It's just something we've kind of set to be above some threshold.
So I would suggest from my experience that would be something worth investigating. I mean, as Steve and others here know, you get different phase diagrams and different material stability realms depending on what the stress strain is. In fact, one of my pet peeves going back a long, long time is people in the community plot phase diagrams as two-dimensional when really there's three or more dimensions actually involved in a phase diagram, for example. Well, my last comment is going back to your earlier, your charts aren't numbered, so I believe it was your quantum informed, and you were showing it looked like radial distribution curves. And I'll just note that you showed a sharp rise first diffraction peak around 1 angstrom, so that's not molecular. But what it likely is, based on work I've published again with Alan Soper at Oxford et al., is that is a void distribution curve where below say 1 angstrom, at or below 1 angstrom, and that may be also a very interesting parameter that tells you something you may not have thought of before. Over. Thanks again. Good seeing you.
Wait. Are you talking about this slide? Or
Yep, that slide there. It looks like these are radial or molecular distribution.
yes. So yeah, these are not from the RDFs are not from shock. This is from just constant volume temperature simulations.
Yeah, exactly. Yeah, if you do X-ray or neutron scattering experiments, you'll see curves like that. And quite often especially for amorphous materials, you see a first sharp rise diffraction peak around 1 angstrom. That's not molecular. It's actually describing the void-void distribution.
Okay.
That goes to a paper we published on phosphorus quite a few years. I'll send you the. Oh, one last comment, by the way. Some years ago, just as a proof of principle, we took some TATB and shocked it in a diamond alpha using, again, ultra fast shock, so ultra high strain rate shock waves. And we designed the thickness of the samples between the two anvils, so we can actually, and working with Riyad Mana, predict and quench rapidly intermediate products that you could not see from traditional experiments to go all the way down to ambient conditions. So yeah, controlling quenching rate is also highly useful, and you're working on that, and that's great. Thank you.
Yeah, thank you.
Roma, please go ahead.
Hi, Rebecca. Great talk. I learned a lot. I was wondering if you're able to use chimes to predict or understand hysteresis at all.
So I want to say yes, but I want to make sure I understand what kind of hysteresis hysteresis due to what?
Yeah, I'm kind of specifically just in the static compression realm. And one of the materials that I've worked on has a structural transition, and then on decompression has hysteresis, so it stays in that structure to a different pressure than what it transformed to. So yeah, I guess I'm just wondering if your program is able to catch that and also maybe explain some effect of it.
Yeah, so I'll go with yes with a caveat, which is there's a reason that I like to study shock compression specifically, and it's because everything happens on relatively short timescales. So even though this method allows us to move beyond the timescales that quantum-based methods can achieve, it's still not going to be the sort of timescales that you would necessarily experience during a static experiment. So I would say what we would be able to do is say, we could model the compression, and we could, drop the pressure and see what happens. But there'd always be the question of, well, is it that if a transformation was going to happen, it would happen on a scale just longer in time than we could access in our simulations.
I see. Very interesting. Thanks.
Rebecca, you were mentioning the effect of strain rates. I was wondering if, for example, you would have a different possibility for tuning how these nanoparticles are formed if you use something like shock ramp compression.
Yes. Yeah, so I think that could totally have an impact on things. It's not something we've explored yet, but it's certainly on the to-do list.
Yeah, there's somebody in our center who's working on that, developing that platform on Z at Sandia, and some really interesting possibilities for controlling, controlling pulse shapes and that sort of thing.
Yep.
But I suppose that's a huge new space, right?
Well, yes, but at the same time, I think that one of the cool things about these simulations is that we could directly model the impact of those different pulse shapes on the particles that we get out. And so that would be, like, in the future, one of the knobs we would like to be able to inform on. Or, of course, we can go the other way and you can say, what would happen if, and we can test that out.
Yeah. This is just a chemist's question, really. In terms of your nano onions, is there chemical bonding between the shells?
Yes, that's a
And you've
good
been able
question.
to.
So the nano onions, let's see if I can I'll grab the TEM image, I guess. Yeah, that'll work. So yes, so these nano onions, I wish I have a beautiful, it's a 10 nanometer one. There's so many layers, it's beautiful. But the point is, they are not perfect. And so what I mean by that is there will be defects in some of the layers that will cause a connection between the different layers. But I would say as a rule, they don't need to be like that. It's more a function of when the particle nucleates in the liquid phase, there is just some number of atoms in that particle. And when you quench, it's going to do its best to form these layers with the number of carbon atoms that it has, but there might be more than it needs to make the, like, you're not going to have, like, let's say for the radius, it would want to have 5 layers, but there are some extra carbon atoms. And so it needs to figure out where to stick those carbon atoms. And so that's going to cause some defects in them.
Yeah.
But that's something like, for example, we see that in these sort of simulations. It's something where, for example, the expansion rate might help with that because you might allow time for carbon shuttling between particles that can get rid of those excess carbon atoms causing the defect. So I would suspect the slower you do this, the more perfect those onions would be.
Yeah. Can you say a little bit about you mentioned the HN3 when you were talking about chemistry and nitrogen. Can you say a little bit more about that material?
Yes. So this this guy over here, this is a liquid explosive. So hydroxylic acid is used in the synthesis of azides quite frequently. And so it's not a great substance to work with because it's extremely sensitive to shock. And if you accidentally introduce bubbles into it, it becomes even more sensitive. So that's kind of why we were looking at this. But yeah, so in this simulation, that bubble is quite literally like a void that you would have in a fluid.
Interesting. Wow. Yeah.
Yeah, incidentally, when I was in grad school, there was a lab that had an accident related to this compound. So it's one of those things where being able to characterize the sensitivity of this material is it's important from a chemical safety perspective.
I bet. Okay. Yeah, Professor Santore, please go ahead.
Do you hear me? Okay.
Yes, we do.
Yes. Thank you for your presentation. And one general question. These shock waves that you produce, I think that they are like the acoustic mode of vibrations of crystal lattices. Somewhat. My question is, do you think in your simulation that with this strong compression, there could be an interaction with the lattice vibration of molecules inside the crystal that could drive one reaction instead of another? Can you introduce this coupling of the elastic wave, the shock wave that you produce with the lattice vibration mode of the crystal?
Yes, that's absolutely a thing that can happen. And I mean, the way that shockwave propagates the material is going to be dependent on things like like if you're dealing with let's say, a molecular crystal, the orientation that you have the crystal is going to impact that sort of communication. So yeah, there can be coupling between those vibrational modes. And so that, I mean, it's something interesting to understand, especially for these explosive compounds in terms of like what's the mechanism of the sort of shock-induced initiation of the compounds.
But the frequency of these shock waves?
Right. So in that case, the idea is so vibrational uppumping, right? So you have the shock wave represents sort of a concerted particle movement. So you're sort of dumping energy into one vibrational mode. That vibrational mode can communicate with another vibrational mode, and you kind of work your way up the frequency chain. So that could happen, yes.
Okay. Thank you.
Okay, are there any further questions for?
I'd like to have a question if possible.
Yes, please go ahead.
This is Arjanal from APS. Thank you, Rebecca, for this beautiful talk. I was wondering if you are planning any picosecond experiments at the X-ray free electron laser.
Not at the moment. I think where we're at right now is that we had this really awesome joint experimental and simulation effort that kind of kicked this off, which is what I talked about in the beginning with this project right here. Ooh, where's my cursor? This project over here. I think this opened the door to a lot of questions that we need to answer from a simulation standpoint before we can say, hey, this would be a really interesting experiment to try. So right now we're kind of mapping out that space. And I'm hoping absolutely in the near future to kind of go back and propose some potentially interesting experiments.
Well, the time scale you are at the picosecond level matches something like LCLS or XFEL, and perhaps it might be possible to do these shockwave experiments there.
Yes, absolutely.
Thank you.
Okay, are there any further questions for Rebecca at this time? If not, then please join me in thanking Rebecca for a really terrific talk, a nice tour through her recent work, and some we're looking forward to further developments. So please come back and see us again.
All right. Well, thank you all once again for having me. This has been wonderful to talk to you all.
Thank you very much, Rebecca.